Okay, so I'm going to talk about program verification for the Linux kernel, potential costs and benefits. This is work with my colleagues Kizuki Nishimura and Jean-Pierre Lozy. So the Linux kernel, I think everyone in the room is familiar with it. It seems reliable. Probably many of you have servers that have been running for many years, but actually it's full of bugs. Anywhere you look, there's more bugs. Some of these bugs fit very well-known patterns, use after free, null pointer dereferences, all these kinds of things. There are tools that have not succeeded in eradicating all of these bugs, but are at least continually finding them. On the other hand, there are other bugs that are very specific to a particular algorithm. You're expecting your algorithm to work in a certain way, but it isn't. It's doing something else. It's not necessarily going to crash. It's just going to run in an undesirable way. So for those, our question is maybe we can help figure out where those bugs are using program verification. So the idea of program verification is that you can write down a specification of what you expect the function to do, and then you can mechanically check whether the function actually does what your specification says. Yeah, this is what I say here. So the idea is you can think of specification as a form of documentation, but it's not English words. It is some kind of formulas that some kind of tool will understand. It's somehow unambiguous. So the positive aspect of this idea is that if you think about things hard enough in order to obtain a specification, then you might see some inconsistencies, bugs, missed optimization opportunities, and so on. And then once you have finished with that task, then you obtain something that is clear, unambiguous, machine checkable, and so on. On the other hand, creating these specifications is admittedly often very hard. And then the problem that we're going to discuss later on, which is probably a kind of an obvious problem in the context of the Linux kernel, is how are we going to maintain these specifications? Because the Linux kernel is changing all the time. The specifications are supposed to be describing what the code is doing, but 1 week later it'll be doing something different and the specifications will be out of date. And then the third problem is maybe the specifications are just wrong. They are kind of, you will see later, they're kind of complicated, formal things. They're not necessarily easily understandable for humans, and so you might write down something that is different than what you intend, and then you will check that your code does this different thing, but that's not really a success. So I just want to emphasize, I try to emphasize this when I talk to actual kernel developers, this talk is just an experiment. It's just something we could think about it. It's not, I don't intend or I'd expect that you all run home and write specifications. I won't be disappointed if you don't. The idea is to think, just see what we can do in this direction, see if it's promising, see if it's worth thinking about more in the future. So don't think, I don't want to write a bunch of formulas, let's run away. But just think about what would happen if we actually did. So here's a simple example. This was presented in Linux Lund a few years ago. Here we have the swap function. Very simple function. I think you're fairly convinced that it works. Sorry. And we want to think about what properties we expect this function to have, what properties might we want to verify that this function is actually satisfying. So basically, we have two inputs, P and Q. These are pointers. We want to swap the values that these pointers reference. And so if we assume that P and Q are actually valid pointers, then the final value in P should be the original value in Q, and the final value in Q should be the original value in P. So these are English words that describe what the function is supposed to be doing. So what I mentioned before, we're going to write some more formal specifications. We're going to use some tool to check that the specifications match the code. So before we start on writing the specification, we have to figure out what tool we're going to use. So we are using a tool which is called framacy. You annotate the source code with preconditions and postconditions. Preconditions describe how things are on the way in to the function. Postconditions describe the state that should exist on the way out. And then framacy will analyze the code line by line and figure out what the code is actually trying to do, and then it will check that the specifications match what the code is trying to do. That will be done by some SMT solver that does things automatically, in quotes at least automatically, and then you will have something that can be checked automatically in the end. So what we want to do, we have our function here on the left, and we want to write our pre and post conditions. So our preconditions were that our pointers are valid, that they point to actual locations in memory that contain some values, that we can read them and write them. So this is fairly straightforward. We just say requires, and then P is valid and Q is valid. That means it's both readable and writable. So that's going to talk about our inputs. Now we need to figure out what our output should look like. And remember, we expect P to contain the value of Q, Q to contain the value of P. So the first post condition is going to be P contains the value of Q. So you say ensures to say that it's the post condition. It's the property that the executing the function should ensure. And you just say star P is old of star Q, because variables have different values at different times, and you have to be able to refer to those different values. You can't say star P equals star Q, because that would be the values at the end of the function. We want to refer back to the values at the beginning. So you can probably now guess what our other post condition is going to be. We want that star Q is equal to the original value of P. So this is, we put it all together, this is what we end up with. We have this signs thing. No, that's not what I wanted to do. How do I, is there a pointer here? That's the middle one? Okay, sorry. Let's fix this here. There we go. We had to, this assigns thing, you always have to say when a function modifies some variables, which variables it modifies, otherwise it assumes that all variables have been modified, which is not what we want here. So then we can, that we've now written our specifications, now we can run framacy, and it prints out a bunch of mysterious things, but the important part is right here. We have 10 things that we're supposed to prove, and we actually succeed in proving all of them, so everything is good. Okay, so that was a very simple swap function. What we're really interested in is the Linux kernel scheduler. This comes from some sense of frustration that we don't really understand what the scheduler is doing. It has many streams of evolution. It's not clear that all of these streams of evolution are actually communicating with each other somehow. Things are changing. Other people expect that some invariants are respected. They're no longer respected, and so on. So the idea is maybe if we actually write down what the specifications are of the different functions in the scheduler, maybe we will at least learn something. Maybe other people can look at them and figure out what those functions are supposed to do. And maybe we will notice when some of these invariants are broken. So that's kind of the high-level goal of this enterprise. Basically here, for the specific task that we're going to do here, we'll take the original C source code of a single scheduler function. We're starting very small. This function will refer to various other helper functions. Some of these helper functions may contain actually vast amounts of assembly code or something like that. They're extremely difficult to analyze. There's many aspects of that assembly code we don't really care about, and so we're going to write some simple functions that kind of behave in the same way. And we will use framacy, the tool that I mentioned previously. In this, we are interested in the algorithm. We are interested in kind of the minimal ideas, like what is this function supposed to be doing? A lot of work in verification is devoted to dealing with concurrency. Concurrency is an even harder problem for humans to deal with. That's not what we're doing here, not because it's not a hard or interesting problem, just because we want to actually succeed in doing something. So we start small. And the same thing for memory. We're just going to assume that we don't have null pointers or memory that points to on top of other things in strange ways or anything like that. So these are hard issues, but developers can make mistakes without those issues. So our function of interest is called should we balance. Should we balance is sort of the gatekeeper into the load balancer. It is, you have many, basically on each tick, you have many idle CPUs that may be calling the load balancer at the same time to see if they have something that they can steal. It's not really desirable for them all to steal try to steal at the same time, because then they will all try to steal the same process, or at least there's a high chance of that. And you'll have some task that is bouncing around the machine, which is very undesirable. So the goal of this function, should we balance, is to see if a particular idle CPU should be allowed to do load balancing at the current time. So this function is not new, it's not old. It was first created in August 2013. It was extracted from some other parts of the scheduler. The first patch was completely incorrect, but that was a situation that did not last very long. Before it was actually part of a release, the problem was corrected. And over time, there have been about 10 changes, so basically in about 12 years, about 10 changes. So it has changed a bit, it hasn't changed excessively. We chose this function fairly randomly as a starting point, but the interesting aspect of it is that it had evolved a bit recently when we picked it out, and so it seemed like there might be some interesting things to do. So the code, basically it takes an environment, and this environment contains some information about the general CPU state that the load balancer has collected. And of course, the most interesting piece of information is the CPU that's trying to do the stealing at the current time. And what the function is going to do, it is going to, it's a little bit strange. It has a loop that somehow elects a CPU that is allowed to steal, and then it compares that CPU with the current one, and if the result is true, then the result is true, and if the two CPUs are different, then the result is false. So here's the original definition from 2013. You can see the first part here. This is the environment that contains various information you can see in different places, notably the CPU that's trying to steal. First part of this is just to check if the CPU that's trying to steal is newly idle. So there's the sense that if it's newly idle, it'd be good to get some task to run on it very quickly, so it always gets to steal. If it's not newly idle, then we have most of the interesting part of the function. Here we have a somewhat complicated looking loop. Basically, what we do is we have 3 different masks, and these are going to describe what CPUs we can steal from. So some of this complexity is just due to the fact that the Linux kernel offers a for loop that will intersect 2 masks, but not 3 masks. So we intersect our 2 masks, and then we have another if down here for the 3rd mask. Basically, what's interesting is that if we're going to iterate over the CPUs, if the current one we're looking at is not idle, then we just want to go around the loop again. So we have a continue. That's not one of interest. We're looking for the first idle one. And that one, the first idle one that we find is the winner. That's the one that is going to be allowed to steal. So if normally we just like spin around this part of the loop as long as the CPU is not idle. Once we find our idle one, we store it in the variable balance CPU. And if we manage to escape this loop without having set balance CPU to something meaningful, then we have some other function here, and that we're just going to pick that one. And then we come to the part of the function that is incorrect. Because this is the original version. This is returning true if balance CPU is different from the one that we are trying to steal with. So basically, if we have 100 CPUs on your machine, 99 of them are going to try to steal at once, which is clearly not desirable. This was supposed to be an equal sign. And that was fixed before the code was released. So here's our pre and post conditions. You don't have to study them in detail. Basically, we have 3 aspects here. This is a bit of new syntax. Primacy allows you to describe behaviors, which are kind of different things that the function may be doing. So one of them is the newly idle case. That you can probably read that one. If on the input we are newly idle, then the result of the function is going to be true. And the other 2 are for the case where it's not newly idle, and the first one is for the case where we do find an idle CPU, and the second is for the case where we don't find any idle CPU, and we go through the whole thing. So, I don't know, my thoughts of like how could we integrate this kind of thing into Linux kernel development? Maybe we would have to go out and hire a verification expert to write the original one. Or maybe people would get used to this funny notation. Or maybe we could come up with better abstractions so you don't have to look at all of these little squiggles and figure out what they're doing. Another thing you have to do is you have to write loop invariants. Anytime you have a loop, the verifier has no idea how many times you're going to go around it. It's very complicated to figure out some kind of invariant that describes every iteration, so the human has to do that as well. This one is not very complicated. Basically, the important part is that all the CPUs that we have seen so far up to the point of the loop index, which is CPU, they are all not idle. As soon as we come to idle one, then we leave and we return that as the result. So now we're done with all of our specifications, and Fremacy proves this in under 1 minute. So that's all pretty good. We had a pretty simple function. We wrote what are, with some experience, are pretty simple specifications, and it all runs pretty quickly, and it says yes, and we're good, and we're done. Move on. So the problem with all of this nice story is that, of course, as I mentioned before, the Linux kernel is changing all the time. These are the various different things that have happened to this function over time. If you look here quickly, this is where we were fixing the bug I mentioned. Here, for example, we improved some comments. That's pretty innocuous. In some other places, however, the algorithm has changed. Some optimizations are added. Those are more challenging. On the other hand, some of these versions actually contain bugs. And this one here in particular was part of a release, and it contained bugs. So perhaps we need to be checking this kind of function a bit more. So as I mentioned, as the question is, as the code changes, what are we going to do with these specifications? How can we keep them up to date? So our idea is that since we have an automated tool, and since we only have to provide the input and the output and perhaps the information about loops, if there are any loops, maybe if the function changes in certain ways, for example, if it's optimized in some way or it's reorganized in some way, but the input and the output behavior stay the same, maybe SMT solver will just take care of everything for us and we won't have to work very hard to maintain the verification process. That's sort of the dream. So then we can go through the history of this function, see what different kinds of changes we had, and see what's the impact on the verification process. So as I mentioned before, there's one case where we changed some comments, changed some lowercase letters to capital letters and stuff like that. That's not going to have any impact, obviously, on verification, which is only related to the code. But here's kind of a nice step. Somebody did some simplification, reorganization of the code, and actually this also has absolutely no impact on the specifications because it doesn't change the input-output behavior, it's just some kind of semantics preserving transformation that makes the code simpler. So that's great. This is a place where people can make mistakes, and then maybe the verification, knowing what the function is supposed to do, would help detect those problems. Here's another case where this is all quite simple. People have forgotten that there's some issue here. I think this one has to do with hot plugging. Maybe someone has yanked out the CPU that is trying to do load balancing, so that would be undesirable target. So we have a new condition that's added here that we get a new behavior in the specification, and then because the specification condition, the language is kind of simple-minded, if we add a new condition up here, we have to add the opposite of that condition in all the other cases. But that's fairly straightforward to manage. On the other hand, as we come to the more recent times, some of the changes are more invasive. So here we have this is like quite a big change in the algorithm. This is dealing with hyperthreads. The idea is that actually we don't want any random idle CPU. We would prefer to have a CPU where all of the hyperthreads are idle as well. So we have our existing test. If we are not idle CPU, then we spin around again. That's going to be a complete failure. But if some flags are true, then if the one of the hyperthreads is not idle, we also want to abandon this CPU. But we don't want to abandon it completely because we might not have any CPU on the machine where all of its hyperthreads are idle. So we just want to remember, if we have not yet found an idle CPU, we want to remember about that. And that will be used later on at the end of the function as the fallback if we never find a completely idle core inside the loop. So it's an understandable change. It's a few lines of code. On the other hand, from a specification point of view, it's kind of complex. So here is our loop invariant. Before, we had a very simple, understandable loop invariant that says, basically, for all of the CPUs we've looked on previous iterations, the CPU was not idle. Now we have some kind of huge state machine here where we have to manage whether we have initialized this idle SMT variable or not so far. So if it's not initialized, we do certain things. If it is initialized, the value has certain properties, and so on. So here things got a bit more complex. And I think it took us a certain amount of time to get these things to work out properly. We're not in the 1 minute category anymore. And then someone had the clever idea that, and this is a pattern that happens some other places in the scheduler, which is if you are going to check all of the hyperthreads of a CPU to see if they are idle, like we have maybe 2 hyperthreads, so here's one of them. We've checked that one, then we'll check this one that's later on in our list. And if we iterate further in our list, then we will be checking that one again. So that's fairly undesirable. Doing these checks involves some kind of remote memory accesses, and so we would prefer not to evaluate that one again. So that's what happens here. What we are doing is, if we have failed on this CPU based on all of its hyperthreads, then we want to remove all of those other hyperthreads from the list of CPUs that we're iterating over. So this is very frustrating from a verification point of view. We have 2 very challenging things. The CPU mask and not. So it's taking the CPUs we're interested in at the moment and removing the ones that are hyperthreads of the specific one we're looking at. The CPU and not function modifies its first argument. And modifying data structures is very, very complex for these verification tools. And the second issue is that actually we're reading this argument, and writing into this argument, and actually these 2 are the same. So we have aliases, and you have to notice that one of the pointers is to the left of the other pointer somehow, and so your data is still okay even though you're writing over the values. And this took us actually like 3 months to get the whole verification process to work out. So that was really hard, and there were times when we actually just thought it was not going to be possible. Like, these tools start getting confused, and you feel like the SMT solvers are basically heuristic things. They're searching some huge space. They may be searching a bad part of that space that's not going to give you your answer, and you don't have any control over that. So there's some things that are true that it will just never find the truth of it. But on the other hand, with all of that work, we found a bug in the code. So again, I don't expect you to really understand these formulas, reading them on the screen like this, but you can see in the specifications of all of the previous ones, we had a if and only if condition, and in the specification, once we get to this one, we can't prove that if and only if condition anymore. We get it in one direction, but in the other direction, we have to kind of relax it with this other noise here. And this is a real bug. Keisuke found the bug and reported it, and it was fixed. And I think I have seen actual traces, execution traces, where the bug happens and where it has a detrimental effect on performance. Maybe not a huge detrimental effect, but some detrimental effect. This is the buggy code. I'll just move on. So this is a summary of what we've seen so far. These are the different versions. The first 7 changes here were quite easy to verify. So it is possible that, I mean, some experiment gives some positive feedback in the sense that it is possible to make some changes and kind of live with the specifications you have or only modify them a little bit. On the other hand, some of these two cases down here were hard and harder. On the other hand, we found a bug that has been lurking in the kernel. It was in a released version for some time. So that was a positive result. So going forward, basically our observation is that complexity in the code are greatly magnified in the specifications, unfortunately. So any extra, we saw the little state machine, any extra things you add complexities in the code causes a great deal of increase in time, in proof time and proof effort for the human. So what we would like to do in the future is develop find out what kind of tools can help us do this better. A simple one is just to isolate the relevant code. If any random function in the Linux kernel is going to be calling many other functions, it's kind of tedious to go and find them all and put them together and so on. So we'd like to automate that. Also writing the specifications, knowing where the aliases are, how the memory relates to each other. You have to describe all of that very precisely. Anything you do wrong will incur huge amounts of verification time. These tools, when things are true, it tells you fairly quickly that they're true. When things are false, it just searches indefinitely. So there's a halting problem issue there. So maybe we can find these aliases. Maybe we can even construct some of these preconditions, postconditions, and invariants automatically, especially for fairly simple functions. And then the last point is about code changes. How can we changes are inevitable. People change algorithms. Some changes are inevitably very complicated, but maybe it can be helpful to somehow inform the user. These changes will be very complicated. You will have to work very hard. These changes should be easy. Maybe you can deal with them directly. And then if there are bugs, how can you use the feedback from the verification to help you identify bugs? And so if you want to see all the code, it's here. You can see what all the specifications look like and so on. So thank you.
We'll take the first question. Sorry.
Julie, are you familiar with the verification efforts going on by Gabriele Palolini and Chuck Wobbler? I'm mispronouncing their names.
No.
So this was done actually last year's in Vienna's Linux Plumbers. We had a safety initiative because one works for Boeing, another works for Red Hat. They're actually trying to for safety critical systems, they need to have a way to verify the code works. So they run tooling to do this. And Thomas Gleichner was involved in this as well. Kate Stewart's involved in this. I think the ELIZA project is doing this. Okay. So what they're trying to do is have requirements. We're coming up with a way of having short-term requirements in the comments above functions. So every function actually has requirements, so they have tooling that could read this requirements and test it. And having it in the comments just above functions should keep it always up to date. So when you change a function, you change if the requirements. So it's all about requirements, not about the implementation details. So basically, here's the inputs, here's the outputs, so you can actually have verification and testing, right? So it looks like some of the stuff actually might be very useful, because one part of the idea is, the hardest part is trying not to have the comments, be ugly, or like the requirements. We're trying to make it so that it doesn't turn off kernel developers, because kernel developers hate requirements. In fact, I don't even want to call it requirements, I call it expectations. What's the function's expectations? So someone that's a kernel developer could actually look at these and say, oh, this is what this function is supposed to do, and know how it's supposed to work, and then they're actually having tooling verified it. Mm-hmm. So if you're not aware of that, I would...
I'm not aware of the specific names of specific people. I'm somewhat aware of that general effort, because I attended the thing that Kate was running at last year's Plumbers.
Yes.
So I would point out that one deficiency of this that no one has jumped up and down. I mean, I had a 10-line function, and we have like 30 lines of specifications here on the
They
screen.
have the same problem, which we're trying to work on a way of fixing.
Yeah. I think that requirements may be, I mean, I'm not familiar with the language that's being used to specify the requirements. These things are extremely low level as compared to what the function implementation is. It's basically kind of restating what the function does, but in a formal language, in a language that's much more verbose than the original C code. I think one might want to imagine, I mean, these things sit above the function definition as comments also. But one might want to imagine something maybe where the requirements are sitting there and these more detailed specifications are somehow off on the side so that people could look at them at different levels.
Right. Then we might be able to have something like that. Have like we're also trying to come up with ways maybe have like short like little make a quick how you say have like a code almost that's sort of readable by English at high level, but then have the details elsewhere.
Yeah.
So something to work on. But yeah, definitely. There's some patches on LKML that actually went out too for.
Okay. Yeah, I mean, there's definitely a lot of work in like how do you express these things in a way that's readable. Actually, I did a different experiment from this one, and I did it twice. The first time, both myself and a colleague, we did it separately, and we both failed because we were writing things in this very low-level way. And then actually I tried it again, and I made some macros that kind of hid things, and that time I succeeded, just because I could read the specifications that I was trying to work on in some sense. So there's definitely some kind of what are the kernel concepts or something that we would like to write, and how can we express them in a particular way? Like in the scheduler, for example, you're often iterating over masks. And so we end up with these huge for alls and integer I and stuff like that. It's all kind of noise after a while.
Sorry?
I just one more comment, sorry, question. So real quick, one more thing I just want to let you know, FYI, because it sounds like you were looking at this. Once I'm done with S-frames, my next project is to kind of re-document the scheduler, like basically so everyone can understand how the scheduler works. So maybe I'll work with you on that too.
Okay.
I wanted to know if you foresee the ease of use good enough to perform a kind of TDD, test-driven development, where you first write the specification and then you write the code. Because I have the feeling that for now you are writing the specs after the code, and could you foresee that we could turn it the way around, which is first writing the specification and then the code to match the specification?
Yeah, so there have been other efforts previously on writing operating systems that are fully verified where they have done what you're suggesting, or at least they're developing the code and the specifications at the same time. Here, my interest is that I just don't understand the scheduler. I mean, I see problems, and they are problems in things that are not fitting together in the right way. And so this is, in some sense, just my attempt to, I don't know, we have these strings, and they are all twisted, and it's my attempt to untwist those strings.
Yeah, about the whole idea of writing specifications, because that's the way we're taught basically in school, and actually I worked at Lucky that we did that. Linux kernel does not do that. Yeah. It basically, the code is the specification, because we want to develop code, everyone reviews the code, so the code is basically, I mean, you come up with, people speak in patches, people speak in the code, and people look at that and they could see, and then actually they try to make it so it looks good. But yeah, no one, if you try to write the specifications and then you implement it and then you put it into the real world, you find out that, oh, you forgot something, or there's like a case that you forgot about that now you have to redesign everything against, and yeah. So no, we won't do that.
Okay. So an issue is that like people are finding bugs all the time, and people are changing the code all the time, and so it's hard to keep all that in sync. Yes.
Did you find the opportunity to spot bugs by just writing the spec? I mean, not even running the tool, just by writing the spec, you find that something looks odd, for example. typically like Steven discussed regarding comments, where in fact in my own code sometimes I figure, because I practice the fact of putting comments on top of the function to explain the entries, output, etc. And often I figure bugs just because the code changed without changing the comments. Sometimes the comments are no longer accurate. Sometimes there is a real bug in the function. And I suspect that by writing such specs based on the code in a different language, you might possibly spot better some inconsistencies or something, some strange patterns, I don't know.
Mm-hmm. Yes, so actually all of the bugs we have found have been from writing the specs. The tool does not find bugs for you. The tool verifies that what you have expressed corresponds to the code. It will say yes if you do that. It will say, I don't know if it does not do that. So it's in designing the specifications, like the bug that we've mentioned here, it's like my student, he made a tree. It's like, if we do this, if we do this, if we do this, if we do this, yeah, what is the result supposed to be? And then he was planning to write the specifications based on that, but actually the result did not turn out to be the way it was supposed to be.
I see, okay.
So it's sort of a different perspective on your code that, like you're saying about the comments also, it makes you think about your code in a more exhaustive way. Then often it's hard to test the code in such an exhaustive way, or it's hard to observe the results in such tests. Because we're not with cases that are going to crash. We're with cases that are going to have subtle, undesirable performance behaviors.
Sometimes you can be fooled by some patterns in the code because they are common, but they do not apply to this specific part.
Exactly, yeah. Yeah.
Okay.
So why do you think the tool did not find the very first bug between version 0 and version 1?
Because we knew that the bug was there and we wrote the specification.
Oh, okay. So it's a bug in the specification.
Okay, it's like we know there is a bug in the code. We write a specification that corresponds to our understanding of the bug, and then we verify that's bad specification against the bad code. And then we know that at least we have understood the bug.
The bug was written in 2013.
Yeah.
Yeah, I mean, certainly the bug was written long before we started doing this work also, so.
Okay, thank you.
Hey, I've been doing a lot of this kind of testing in much higher levels, like web application development, where it's super easy, and here admittedly it's really hard to follow sometimes. How well do you, from your experience, how well does it scale? So, like, I don't know, I assume you have like a team of people working on this stuff. Like, can you give some rough idea of, you know, how well you can increase coverage over time or something?
I think we started this project in, I'd say 2 years ago, maybe. So this was the first function we worked on, and then we have worked on a few other functions since then. Not really full-time, but still, it's, at the moment, it's not scaling up very fast, I agree.
Okay, thank you.
Yeah, I'm curious, so there was one optimization, the earlier return, that you didn't have to express in the from a C description. And the second optimization, the optimization that skipped checking the other hyperthreads in the core that caused you a lot of work. I'm wondering why you had to express that in from a C, because it wouldn't actually result in any change in the outcome of the function.
Yes, it does.
It does?
Yes, because it's a hyperthread issue. It's like if you have, maybe you have 4 CPUs on your machine, 0 is matched with 2, 1 is matched with 3. Maybe you could have 0 that's idle and 1 that is not idle.
Mm-hmm.
And so previously 0 would be the result, but now if 2 and 4 are both, or sorry, 1 and 3 are both idle, then now 1 will be the result. So it changes the result.
Right, but I was thinking of the, so that was the change in behavior where it's, well, the one that you've got there, but then there was the later change where it skipped.
Okay, I see, I'm sorry, okay, yes. The reason, indeed, I believe there is no change on the pre and post conditions of the function, but the problem is that we have to write loop invariants. And so, because this happens inside the loop, then we have to express that inside the loop invariants. I mean, basically, what this line of code here is doing is it changes the set of things that we are iterating over. So that has kind of a catastrophic effect on the behavior of the loop.
Yeah, I'd forgotten about having to describe the loop invariants. Thanks.
So I have a questions about the loop invariants. So are there something that if you write it wrong, the tool will also tell you that either you wrote it wrong or the code doesn't correspond to it, or if you write it wrong, can you mislead the tool to give you wrong results because it cannot verify the actual code of the loop against the invariants? And you are using them.
If you write the invariants wrong, it will say, I don't know.
So it cannot give you like false positive results?
No, it doesn't give you false positives, but it doesn't give you any feedback about what went wrong either.
Okay.
So it's basically, I mean, what you are dealing with is some kind of heuristic tool, searching tool, and you have no idea what it's going to do. So if it fails to prove the thing you want to prove, you have no idea whether it might be helpful to have more time, or whether it might be, or if you need to change, if you're trying to prove something that's false, that will never succeed at. And so if you believe in what you are doing, you tend to increase the amount of time that you give to it. And then you have to wait longer and longer and longer to find your failed results. Basically, the only thing you can do is you can put asserts for things that you think it should be able to prove. And if it is not able to prove those things that you think should be very simple, then you might have some intuition that something is going badly wrong. But it's kind of like, C code, and you put prints and you try to see.
Okay, thanks.
So if you're successful and like we managed to prove the entire scheduler, do you have an idea about how long that might take to prove?
How long it will take us humans to write correct specifications and prove them, or how long will it take the tool to say yes or no?
Well, what I'm really asking is, if somebody submits a patch to the scheduler, and we wanted to reprove that the scheduler still works after that patch, how much machine time would it take to do that?
Completely randomly, I would say, I don't know, 15 minutes or something. I don't know. Depends how much you parallelize it. Depends on how big a machine you buy.
That's much better than I was fearing, so thank you.
Maybe 1 hour, I don't really know.
Still, I fear the answer might be 3 to 4 weeks, or something ridiculous.
No. Okay. Basically, once you have specifications that are correct, it can typically prove them quickly. The problem is the human time in advance to make those specifications correct.
Thanks. Thank you for the presentation. I have an idea on top of my mind is a little bit abstract and a little bit fuzzy, I would say. If you have specification, we could imagine a tool that implements the specification for us. I mean, not writing the C from the specification directly.
I'm sorry, I didn't hear.
Yeah, the idea is like, as we have the specification, we could have a compiler creating, or not a compiler, but creating the C code for us, doing the implementation for us.
Yes, perhaps, yeah. I mean, that goes in the other direction that was suggested, to write the specification first, and then maybe we can generate the code from it. But the problem is that we won't like that code, and we will test it, and we will change it.
Yeah, sure, but we can, we can create a BC LLVM bytecode, for examples.
I mean, the specification is kind of forced to be specific enough that you could probably.
Yeah, but you in the specification you give the bounds of loop, for example, and you give the bounds. You're giving the scope of what the function should validate.
Yeah, I think unfortunately, I think there are some cases where the specification language is not rich enough to express exactly what's happening in the code.
Okay.
And so if you start out with those kinds of specifications, you might not actually end up with the implementation that you want.
Yeah, so basically today is limited, but we can imagine remove this limitation within time. So.
Yeah.
Yeah. Okay.
Yeah, it's something to think about.
Yeah. Okay. Thanks.
Can the specification language handle cases where the function mutates some more global state? Like if some state is being passed in, it changes it?
Yes. Yeah.
Okay.
We saw the assigns previously, and so you say what part of the memory it assigns.
Okay.
It updates, yeah.
Yeah, just a remark is like your specification language is very close by HDL, like a specification for ASIC and FPGA, because it's already assigned and things like that we specified. So it's very close by this language, like HDL language.
Okay,
So
yeah.
well,
I mean, we didn't invent this language. I
I
think it's a fairly standard language for different specification tools, or they
Yeah,
have languages that are very similar.
is
to
one
what
way
we
of
found
the
here.
abstraction. Yeah, I agree.
Yeah.
I was wondering whether people writing unit tests for the various functions, for example, inside the scheduler, would be helpful to your work of analyzing what goes on inside a specific function, just to give you examples of corner cases, for example. So is unit testing something that's helpful to your work in like writing the specifications, for example?
I have not had experience looking at unit tests. Intuitively, I'm not sure, because the specifications have to cover everything. So if the unit tests were perfect already, maybe it would be helpful, but I don't know.
Thank you.
Is this frame a C package in distribution so that you can try it and test it easily? Or?
Yes.
Okay.
It's written in OCaml, and so there's a tool called OPAM, and then you can say OPAM install from a C, and then you have it. But I think you can also just get it by, maybe it's in, Ubuntu or whatever. Sorry?
In Debian, you know if it's there?
I don't know. You can see.
I'll check.
But it's, it's developed by this CEA. It's something that exists for many years, and it's regularly maintained and so on.
Okay, thank you.
Okay, thank you.